Hello, Mr. Ari, are you alright?
Yes.
Okay, so we talk about quick sort, yeah? Quick sort. We talk about merge sort before, yeah? And we talk about the bubble sorting. And yesterday we talked about what? Selection sort, right? Yeah? Okay. So these two are simple sorting algorithms. Simple. Yeah? Simple means they're easy to implement, right? But on average, their time complexity is O(n) square quadratic. These two are the most efficient sorting algorithm. On average, their running time is O(n) log n, right? Yeah. So that's what we have if we call the array.sort function. Okay. Bubble sorting, selection sort. Okay, so now let's just do a quick review of how these, what kind, how does this algorithm work? Okay, so for example, we have quick sort. Yeah, we let's say 5, 4, 7, 6, 1, 2. Quick sort. We randomly pick a number as a pivot. Yeah, as a pivot, and then we try to put all the elements smaller than the pivot. Yeah, in the left, and that's the pivot. Yeah, could be many, right? And then all the elements that are bigger than the pivot on the right. So then we recursively sort the left and the right, right? But in the worst case, if the array is already sorted 4, 3, 5, 4, 3, reverse sorted, right? And then every time you pick the first one, what happens? So in this case, you don't partition into two. You always have all the elements on the right hand side. So in this case, what happens? The time complexity will be downgraded to O(n) square. Okay, pivot. Merge sort. Yeah, we know how to merge two sorted lists. So the idea is to divide the list, divide the array into two halves, equally two halves, and then we recursively sort the left part and sort the right part, and then we merge it. Yeah, the time complexity on average O(n) log n. And worst case, best case, worst case, average case for is O(n) log n. Okay. Bubble sorting. Every time we bubble out the biggest number to the end, right? For example, like 5, 4, 3, 2, 1. So what happened after one round of bubble sorting?
4, 3, 2, 1, 5.
Yeah, so every time we swap, if it's bigger than the next one, right? So that becomes 4, 5, and then 5 keep continue to swap it. So 4, 3, 2, 1, right? So bubble sorting, the best case is we can improve it if we can add a check. If there's no swap, then we can terminate the loop, right? So that in the best case, is the time complexity is O(n) for the improved bubble sorting. In the worst case, average case is O(n) square, right? Selection sort. So 5, 4, 3, 2, 1. What's the selection sort?
Putting the smallest number at the front. So it's 1, 4, 3, 2, 5.
Yeah. 1, 4, 3, 2, 5. Okay, so every time we pick them, we swap the minimum value to the front, right? So on the left hand side is sorted. On the right hand, the right subarray is unsorted. Every time we pick the smallest element from the unsorted, and we swap it to the front, right? To the front of the unsorted, right? That's the selection sort. Okay, so today we're going to talk about another sorting algorithm, which is called what? Okay, one more thing before I forgot is selection sort. The advantage of selection sort is that we can the number of swaps is no more than n, right? Am I right? Because if the swapping is quite expensive, then we can choose the selection sort. Because bubble sorting could be, right? It's always swapping. If that operation is very expensive, then that might not be very good, right? All right. So that it has different advantage. Okay. And then we talk about today. We're going to talk about another simple sorting algorithm. Okay. Simple sorting. Simple means easy to implement, easy to understand, right? It's called insertion sort. Okay. So what does it mean? Look, if we have 5, 4, 3, 2, 1, okay, like that. Okay, so how do we sort it? So at the beginning we are here, and then we find we want to put this number, right, So at the beginning we have one element which is sorted here. Alright, and we start with the second element. How do we put the 4 into the front? Right? We want to insert this value to the front, to the sorted, right? So it's 4, 5, right? 4, 5. Now I want to put a 3. I want to put a 3 in what cases?
3 at the very front.
Yeah, the front. Okay. So how do we do it? Look, every time we pick this number and then we want to swap it, we want to insert it. Okay, this is called insert. Insert it in the front of the list. But how can we do it? Look, 3. So when this 3 is smaller than 5, right? When 3 is smaller than 5, so first of all we take the number key equals 3. We remember it, right? We remember it, and then we move it. We shift it. Like, look, we shift it. So what happened is that 5, I put it here. 4, I put it here. Okay, and then I have a space for a 3, so I put a 3 here. Okay, another one, 2. 2 here. So I key equals 2, right? Key equals 2. So now 2 is here. So I want to put it in the front. I want to insert it in the right place of the 3, 4, 5, right? It could be in the middle, but in this case it's in the front. So what should I do? Look. So remember, I already take the value 2 here. So I move it. Alright. Look, that's the magic, eh? Move the 5 here. Alright? And then move the 4 here. Yeah? I move the 3 here. So and then I change this here to 2. Make sense? Yeah? Does it make sense? Okay, I want to give another more example, okay? How about 1 here? I put a 1. Now I want to put a 1 in the list of these.
But what are the very front?
Yeah. But all the elements will be shifted 1 position to the right? Yeah? Okay, so how do we insert it? How do we insert it? Look, we remember, we know the current element is 1. We want to put a 1 in the front. So like, look, 1 is smaller than 5, right? Yeah? 1 is smaller than 5. So what do we do? So this value, next value would be 1. Will be copied over. The value will be 5. And then copy over 4. Yeah? So basically you move it. You move all these elements 1 position to the right. Okay, now here. So this is the right place because it's at the beginning, right? So I put a 1 here. Make sense? Yeah? Okay, then let's try another example, okay? Just to make sure you totally understand this. Insertion sort, okay? Let's say 0, 1, 3, 5, 4, okay? Let's say. Now, I'm here. I want to put the 4.
4 before the 5.
Yeah, before the 5.
And after the 3.
Maybe put a 2 here. I want to put a 2, okay? So it's in the middle, right? Yeah, so but how, look, how? I compare to this. This is smaller than that, right? So I need to push this 5 to the right, right? Yeah? So it's pushing 5 to the right, I can just write this value as 5, right? And now here, and then now I need to put here 2. Right? 2 is smaller than 3, so I push 3 on the right. So yeah? 2 is bigger than 1, right? So in this case, what happened? I don't shift it. So I just need to change this value to 2. Yeah? Make sense? Does it make sense? Okay. So let's go get to the code, okay? And you tell me. Define insertion sort, and then we have let's call it A. What do I miss?
Hold on.
You're not even looking. So n equals length A. So let's say we need to go through the array first. Yeah? For I in range, let's start with the second value. Yeah, 1 to n. Look, so this is array A, yeah? A equals array 1, 0, 2, 5. So I start here, yeah? Because at the beginning we have already one list, the sorted list is length 1, right? We want to put the element in that. So now I need to remember what value is it. Key equals the I, right? So key is this value. Key is the actually let me think about it. Key is AI, right? Yeah. Key is the AI. Yeah, exactly. Yeah. So now J. Let's say J equals I plus 1, while J equals Y plus 1. J is here. J is here. So Yj, actually J is I minus 1. Yj bigger equals 0, right? And the key is smaller than, as long as the key is this value, this value is smaller than this value, yeah, Aj. Then what do? We need to set this value, J plus 1, Aj plus 1 will be equals Aj. That's we shifted it, and then J minus equals 1. And at the end, we need to set the Aj, right? We want to set this value, Aj equals key, am I right? Make sense? So, there might be a problem. Actually it's Aj plus 1. Okay, let me just double check, because this algorithm is not so easy to make it right at the beginning. We have to check the boundary, etc. Right? Let's double check. So if you're looking this, what's the time complexity if you look at these?
I think it's
Is it right? J smaller than Aj plus 1 equals Aj, J minus equal 1, Aj, yeah, the next value needs to be set to the key. Okay? Yeah, I think I got it right, yes. Let's just run this, okay? Let's just run this, and we can correct the mistake if we have. 1, 3, 5, 7. Let's say 1, 3, 7, 5, 2. Okay? Yeah? N will be equals to what? 1, 2, 3, 4, 5. 5, right? Yeah? I will be from 1 to n, right? So I will be in this event, at the beginning it will be here, right? J will be I minus 1, so J is here, okay? J is here, right? Yj is bigger than 0, right? J is bigger than 0 or bigger than 0? Yj is bigger or equal than 0, right? Yeah? And key will be equals to AI. Key will be 3. Key will be 3 at the beginning. So key 3 is smaller than Aj. It's not, right? It's not. Okay, so look, then this loop, this while loop will not be executed. And then the next will be Aj plus 1. Aj plus 1 will be this one equals key. So it basically set it to 3. Yeah? Okay, now move to the next one.
What's n?
Here, the number of the element.
Okay.
Maybe this is not a very good example, yeah, because this is already in order. So look, if it's in order, this does nothing, yeah. If it's this in order, if it's 1, 2, 3, 4, 5, so what happened? What's the best cases? This is already sorted. So look, if this is in order, so can you tell me, do we go in here somehow if it's already in order? Yeah, because j is I minus 1. So we always checking the previous value. Yeah, if the previous value is bigger than the key, right? It's never true, right? Array. Yeah, for a sorted array, key is always bigger. Key is this value. Yeah, key is this value, and we are starting checking the previous one. Key is always the bigger than the previous value. Right? So this key smaller than previous value, never true. It's never true. So this while loop never gets executed. So what does it mean? We all, in the best cases, what is time complexity? Oh, yeah, it's like the bubble sorting. Yeah, bubble sorting we have added a check. If there are no elements are being swapped in this round, it means that the array is already sorted. Then we can terminate it, right? But here, if it's array is already sorted, then this while loop never gets executed. And then if the best cases is on, right? And in the worst cases, look 5, 4, 3, 2, 1, right? So look, so 4 is right is smaller than 5. So basically I need to squeeze the previous element for the space to put in the 4. Do you get it? Mm-hmm. Okay, so look, for example, look here. I'm right here, 5, right? Alright? 5. So look, this is already sorted, right? Here, 1, 3, 7 is already sorted. So now I want to squeeze. Check the previous one. Squeeze. If it's smaller, so look 5. I miss this guy. Okay, says okay, I'm smaller than you. You need to make a space for me. So he will squeeze this 7 to the right. Yeah. Okay. Yeah. All right. Okay, 2. Smaller than 7, yeah? You then say, okay, squeeze for space for me. 2 to the 5. Still smaller. So it's like you're waiting in the line and then you're always checking. Okay, 2 is smaller than 5. Okay, please go behind me because I'm smaller than you. Yeah? So check the previous guy. It's still smaller, right? Okay, make space for me. Yeah? Got it? Yeah? But it's not doing one by one, it's doing all at once. Okay, so let's do, so it's not, look, 2 here. So you will check. Okay? Smaller, go to the right. 5, I am still smaller, I'm still in the front. 3, yeah, I'm in front of 3. 2, no, right? So okay, I'm here. Okay, so for all other elements, so needs to be 1 position to the right, right? So these 3 needs to move 1 position to the right, and then you put a 2 here. Make sense? That's what it does. Look, aj plus 1 equals aj. Hey, aj plus 1 equals aj. What does it mean? So look, 5, 7. aj plus 1 equals aj. So what happened? Happened up here. If j is here, so what happened after this? aj plus 1 equals aj. What will be happening? What will happen?
Squeezing.
Okay, j is here. So 5, 7. aj plus 1 equals aj. So what happened after this? aj plus 1 is this one. Equals aj.
That means they're swapping and they're
No, it's not swapping. I just this one. aj plus 1 equals aj. What's happening? aj plus 1 equals aj. aj plus 1 equals aj. So what happened?
They're squeezing.
These will change to
Yeah, 5.
5. And then 2, 5. And then here, aj plus 1 equals key. So because j will be minus 1, right? So j will be here. aj minus plus 1 is here. Equals key. That will be whatever. Okay? Well done, okay? So let's wait. In the best cases is on, okay? Okay, I want to talk about another concept which is called stable. You know the stable? Stable, what does it mean? Stable. What's the word in English?
It's balanced.
Or
horsey thing.
What's not stable?
Not balanced.
Okay, balance. Yeah, balance. Okay, in sorting diagram, stable means that look, if I have 2 value, 2, 2, 2, 2, and right. So if these two, okay, so this green two, if I have this. So after sorting, yeah, that will be 3, 2, 2, 2, 4. After sorting, yeah. After sorting, if this green two is still on the right of the black two, right? It's called stable. Yeah, because they are the same. You basically you can swap it and it's still sorted, right? Am I right? Yeah, but for some algorithm, this will become 2, 2, right? 2, 2, 3, 4, maybe, yeah. Or another kind of algorithm is what? Is 2, 2, 3, 4. So can you tell me which sorted result is stable? Which one is not? Which one is stable? Which one is not? So the original array is 3, 2, 2, 4, and then one sorted array is 2, 2, 3, 4. The other one is 2, 2, 3, 4. The only difference is these two. They are.
Why is 3 and 4 green?
Okay, yeah, that's a good question. No. Okay. So which one is sorted? Which one is stable?
Oh, the first one.
This one?
No, the one.
This one, yeah. This one is sorted, stable. Because the original order is the green 2 comes after 2. And this one, the green 2 comes before. Then actually you are not maintaining the order of the similar, of the equivalent elements, am I right? Make sense? Yeah? Okay, so the bubble sorting is stable, right? So because every time you take a round to bubble sorting the same same numbers, so it's all is stable. The insertion sort is stable. The what? The quick sort is not. The merge sort is stable. The selection sort is not stable. Okay, I tell you why selection sort is not stable. Look. 3, 2, 3, 4. Okay. Yeah. Okay. Maybe this is not a good example. Let's say. So how does the selection sort work? You always swap it, right? You always swap it. You always swap it. So this is 3, this is 3. So let's say this is 2. Okay. So at the first one, okay, let's make this 3. At the first one, you pick the smallest index, which is 2, and then you swap it with 3. Okay. So that's 4. Okay, 2. Yeah. Okay. Look. Selection sort. What happened? What's selection sort? What element do you pick? Which one is the smallest?
2.
Okay, so what happened? What should I do with the 2? Swap it with 3, right? Yeah? So once you swap it, what happened? It'll be 2, 4, 3, 3. Do you see the problem? This green 3 is after black 3. But now
why do you need to swap 2 with green 3?
The selection sort. Look, yesterday we talked about selection sort, right? What's selection sort? You pick the minimum, right? And you swap it, right? So you swap it with the beginning of the unsorted list, alright? Yeah, remember? Yeah. That's how the selection sort works, yeah? Insertion sort today is the squeezing, yeah? The bubble sorting is, every time swapping with the next one, right? Okay, so that's not stable, okay? Because look, after one round of swapping, the green 3 is now becomes in the front of the black 3. That's not stable, right? Right? Make sense? Okay, so let's just list the table for these 3 sorting and that'll be it, okay? What do we have? Bubble sorting. And yesterday we talked about selection sort. Today we talk about insertion sort, right? And at the beginning, last year, we talked about quick sort. yeah, and then merge sort, yeah. This is the 5 sorting algorithm we have learned so far, right? Yeah, alright. Okay, let's say the best case time complexity, average time complexity, worst case complexity, space complexity, and is it stable? Okay, let's just consider this. Okay, yeah. Bubble sorting, best case is O what?
N.
Yeah. Average O(n) square, worst O(n) square, space O1, stable, yes. Selection sort yesterday, best case is O(n) square, yeah. It doesn't average O(n) square, worst O(n) square, space O1. Is it stable? What? No, yeah. Remember that thing, yeah. Insertion sort today, best case is
O(n).
average is also O(n), you know, this is simple sorting, the average and worst is the same, it's O(n) square, okay? Space O1, insertion sort is stable, okay? Quick sort, best case is, quick sort, remember we pick a random, choose a pivot, and then we put the elements before it, smaller on the left, bigger on the right, and we recursively sort both parts. Oh, what's the time complexity for the sorting? You know, it's a
N log n.
right now. Average is still O(n) log n. Worst case, remember over
N square.
O(n) square. Remember, if it's the reverse, yeah, if it's 5, 4, 3, 2, 1, and every time you pick the pivot as the first element, and then you are not making use of this fact they partition into 2 halves, O(n) square. Space, worst case O(n), stable, no. Merge sort, O(n) log n. Average, O(n) log n, yeah. Worst case, O(n) log n. Space, O(n), worst case. Is it stable? Yes. Okay, so let's see. Any questions? So which one do you think is better? Is you like the best? You have different advantage and disadvantage, right? Yeah?
I like merge.
Merge sort because it's quite stable. It's stable and it offers quite consistent performance in the best, average, and worst, right? Yeah. And all these have different, right? Look, and this one is consistently O(n) square, which is very slow, inefficient, okay? And it's not stable. So yeah, I agree with you. Merge sort, and it's very easy to understand. Yeah, merge sort. I have 100 numbers to sort. First of all, I cut into half. 50-50, right? So I don't care how you sort these 50 numbers each. But once you have these 50 numbers, we know how to merge it, right? Merge to sorted list. Do you still remember? And we'll put it together. And for the 50 numbers, we can keep dividing it, right? Into 2 halves. How much for each? For 50 numbers,
25.
Yeah, 25 and then 12, and keep dividing until we top down, yeah? Until we get the one element, it's already sorted. And then we're starting to merge it back, yeah? One element, we know how to merge, right? So we have 2 elements now. And 2 elements, we know how to merge. 4 elements, 8 elements, yeah? Got it? You see, how beautiful is this sorting algorithm, right? You know, there are quite a lot of knowledge about this sorting algorithm, and then there are a few more. But which bit are simple sorting algorithm? 1, 2, 3. These 2 are simple sorting. Why is that? Because the average is O(n) square. It's easy to implement, right? It's usually two for loop, right? Yeah? But for the quick sort and merge sort, it's usually complicated, right? You have to write a lot more code using this. But you know, the modern computer, if you use the array.sort, it's usually based on quick sort. Yeah? It's a mixed sorting algorithm, quick sort and sometimes merge sort. Yeah, these 3 algorithms, yeah, it's just useful to teach you how the algorithm works, okay? Because look, if there are a million numbers, this is too slow. A million times a million, it's too slow, right? Got it? Yeah, okay. That's it for today. Good job. Bye-bye.
Bye bye.
Bye-bye.